In the last video, I showed you the fundamental concept of my low-level graphics framework Ovis. But being low-level has one significant drawback. There is no hand-holding. It gives you the building blocks, but you have to build yourselves. Join me today to find out how I want to accelerate the building of applications and how this hopefully also makes third-party libraries more compatible with each other. As you have probably guessed based on the title, I want to provide a sort of standard library for my framework, which provides commonly used functionality and components that enables other libraries to work together seamlessly. The term standard library is normally used in the context of programming languages. And by the way, once upon a time, Ovis was actually meant to be a standalone language instead of a Rust framework. But this is a story for another time. Back to programming languages. Even in low-level programming languages like C++ or Rust, you don't have to start from scratch. Both ship with a standard library, so you don't have to implement your own string or vector class before you get going. Similarly, the Ovis standard library should include basic render systems that implement common algorithms, so you don't have to write your 1 millionth Bling-Fong implementation. A very different thing in computer graphics are the transformations between different coordinate systems or spaces. When defining a 3D object, you usually do this within the local space of the object. Then you build a 3D scene by transforming the objects into a common world space. When rendering the scene using a camera, you will first transform everything to the local space of the camera, which is also called view space, before applying the projection, which transforms it into the clip space. Each of these three transformations can be represented by a matrix. If you want to know in detail how this works, you can watch my video about egocentric projection afterwards. You can find the link down below or at the end of this video. For the Ovis standard library, I defined three components for the three transformations: world from local, view from world, and clip from view. Where the former is meant to be attached to the object that should be rendered, and the latter two should be attached to the entity containing the viewport. For those who are wondering about these weird names, I created this naming scheme a while ago, where I used a naming scheme where transformations follow the pattern target from source. This way, when I multiply together matrices and vectors, I can immediately tell if the operands are in the correct spaces by looking if the pre- and postfixes before and after the multiplication operator are the same. I like the system a little better when using row vectors instead of column vectors, because then the multiplication order is reversed, and view from world would become world to view, which sounds a little nicer. That said, I stuck with it even for column matrices. What do you think about this naming convention? Do you find it useful or rather weird? Let me know down in the comments. Let's see how this looks in practice. For that, let's look at the vertex shader from the last video, which creates the positions for a single triangle. First of all, let's try to apply the naming convention I just described. After doing this, I noticed the extremely ambiguous naming of this vertex shader output type. Position could mean anything, but paragraph 13.3.1.1.10 of the WGSL standard from the 7th of May 2026 clearly states that it is, quote, the clip position of the current vertex in clip space coordinates. Seems pretty clear to me. And to avoid any confusion for users of my framework, I changed the name of the type accordingly. However, this reveals another inconsistency in this shader. The variable I named world position is assigned to clip position. This should definitely raise some eyebrows. Let's fix that by accessing the transformation components defined earlier, and 3 matrix multiplications later, everything seems to be consistent now. But this addresses only one side of the problem. We are now properly handling the consuming side. But how to create these matrices? Defining these by hand can be very tedious. So I also added some helper functionality for this. First, I added another component called perspective camera, which stores the parameters needed for a really basic perspective projection. Then I added a system which looks for this component and generates the resulting clip from view matrix. Similarly, for the world from local, I created the transform component, which provides an easy way for the user to specify the position, rotation and scaling of any object. And a corresponding system creates the world from local matrix from these properties. And because the view space is just the local space of the camera, we can just take its world from local matrix, invert it, and we have the view from world matrix. Wonderful! Now we have all the basic building blocks to easily handle the transformations between the different spaces. We can move individual objects, or we can rotate the camera, or we can change the field of view of the camera, or we do everything at once. I'm also planning to add some basic camera behavior to this standard library, like this orbital style camera controller you're seeing right now. What do you think? Is that something you would expect to find in such a standard library, or rather be implemented in a third-party library? Let me know down in the comments. And next time I want to get rid of these individual triangles and talk about how to handle more complicated meshes. And after that I have a whole book lying around with algorithms that are just waiting to be implemented. And if you don't want to miss that, please consider subscribing. It really helps the channel, and I promise to upload more frequently in the future. And with that said, thanks for watching and see you soon.